Okay. So, are you there?
Yes, sir. We
Sir.
are.
Yes, sir.
Okay. So, in the mathematical physics, you take your this material. You take out your material.
Yes, sir.
So, the first chapter, what we have, what you have? Can you show me anyone?
Legendary differential equation, sir.
Legendre differential equations are there, no? In that, what we have, what you have, do you know? Legendre differential equations and solutions, and the generating function, Rodriguez formula, orthogonal properties. We have recurrence formula. All these you have, no?
Yes, sir.
Okay. So today, what we'll do is we'll start with Legendre's differential equation and then a solution. Then we'll go along with your syllabus. So what I'll do is I'll share the screen so that it is unable to write everything because it is an online mode. So already I have written all the thing. I'll explain to you. Okay.
Okay, sir.
Okay.
Later on, I'll share the notes also.
Okay, sir.
1 minute. So is it able to see this?
Yes, sir.
Yes, sir.
Yes, sir. We can able to see.
Yes.
Yeah. See here. So this is the first. We'll start here. Legendre's differential equation from. So here, if you see, here we have Legendre's differential equation. 1 minute. I'll take it. So this is the Legendre equation, which we can be defined like this. So Legendre's differential equation as 1 minus x square into d square y by dx square minus 2x into 2x into dy by dx. Okay. So this one.
Your voice is breaking, sir. We can't hear you.
Voice is breaking.
Yeah,
Yes,
I
sir.
don't know. It's only with me or.
Maybe the connection problem here. I don't have it. So here, if you see,
Still, we can't hear you if you're speaking, sir. Sorry.
you won't able to see this one.
Yes, sir.
Yes, sir.
Now.
Yes, sir. We are able to see your screen.
Okay. So you see, actually, it is 1 minus x square into d square y by dx square
Sir, your
minus
screen is
2x.
showing something other. Your screen is not showing Lagrange's
What is it
equation,
showing?
sir.
Sir,
Sir,
some of the
screen is
icons
showing
have been
something
shown
like-
on your screen. Sir.
Yes, yes. Now, sir, it is showing.
My screen unable to see.
Now, sir, it is
Now it
showing.
is obvious, sir.
Now it is okay.
Yes, sir.
Yes, sir. Absolutely.
Yes, sir.
Yeah. Okay. So this is the differential equation which we have. This is 1 minus x square into d square y by dx square minus 2x dy by dx plus n into n plus 1 into y 0. This equation we will be calling it as a differential equation, which is actually the Legendre's differential equation we have. Okay. So in this, we have like n values can be take starting from 0 and up to the infinite value like 0, 1, 2, 3, and so on. It is going to take n values. So here, this is the differential equation we are going to be on. Now, what we have to say is we have to find out the solution for this one, for this differential equation. So in order to find out the solution for this Legendre's differential equation, so we will be assuming solution of this above equation, means for this equation, whichever we have defined here. So this equation is there, no? For that, we will be assuming the solution as follows, like y is equals to x to the power of k into a0 plus a1 by x. Otherwise, we can write it as a a1 x to the power of minus 1 plus a2 x to the power of minus 2 plus a3 x to the power of minus 3 and so on, plus ar x to the power of minus r and so on we can write here. So this is the solution we are going to be assume the differential equation 1. So whatever the differential equation 1 is there, that is the Legendre's equation. For that, we are assuming the solution as follows. So this is we can write this as in this form we can write that is the summation of r is equals to 0 to infinite. Otherwise, we can say that sigma of r is equals to 0 to infinite ar x to the power of k minus r. So this is the solution which we can we take. So equation 2, whichever we have, this one. Okay. So this part, whichever we have, this is a solution we are going to be assumed here. Summation of r is equals to 0 to infinite ar x to the power of k minus r. This is the solution.
So what is k?
So now, what is k?
K.
So it will be coming. So here, I'll explain all those things. So this is the solution which we are taken, and here we have to assume that always a0, the first term whichever we have here, a0. So this is always not equals to 0. Will be always not equals to 0. So now this is why we have assumed y as equals to.
Sir, your
summation of
voice
r
is
equals to
breaking,
0
sir.
to infinite. Breaking. So
Sir, sometime it is little bit breaking, but I think manageable. Sir, sometime it is little bit breaking due to network problem. I think it is manageable, sir.
maybe I don't know signal problem here.
Yes, sir.
because,
Yes, sir. Online class.
Okay, we'll continue.
Okay,
So this
sir.
is the solution we have assumed. Y is equals to summation of r is equals to 0 to infinite ar x to the power of k minus r is the solution we have been assumed. Now what we'll do is, now in this equation 1, we have all the terms like y term we have, dy by dx is there, d square y by dx square is there. So in order to get all the values, the solution we have assumed as y is equals to this one. So we should know dy by dx as well as the d square y by dx square in order to substitute in the equation 1. So what we are doing is we are differentiating this equation 2 here. That is the first derivative we have. Derivative dy by dx. Differentiating this equation with respect to x. We are going to get it as equation 3, which we have is summation of r is equals to 0 to infinite, right? Summation of r is equals to 0 to infinite. Ar is the first one, whichever we have. This a minus r, whichever we have. So that differentiation, you are going to get it as a k minus r x to the power of k minus r. So this differentiating.
We can't hear you, sir, if you are speaking.
Sir, now, sir, it is completely not audible.
Completely?
Not audible. Sometime you are not audible, absolutely not audible.
1 minute.
Sir, I think if you say little slow, I think if there will be some
No,
net
this
problem.
is a network problem, I think.
If there will be network problem, sir, if you say little slow, I think it can be manageable.
Should I say slowly? Okay.
Yes, sir. Yes, a
Yeah,
little
yeah,
slow.
So now you see, this is the equation 2, which we have assumed as a solution, right? That is summation of r is equals to 0 to infinite we have, and solution we the entire equation which we have here, we can write it as ar x to the power of k minus r. Now we are going to be differentiate this equation 2 with respect to the x. That one we are going to get it as a dy by dx. Okay, we are differentiating this equation y with respect to the x. So therefore it will be dy by dx, which is equals to summation of r is equals to 0 to infinite, whichever we equation 2 as we are writing as is. Now the differentiation of x to the power of k minus r. So the differentiation of x to the power of k minus r, we are going to get it as, suppose if you have a differentiation of x to the power of n, that is d by dx of x to the power of n. What is the differentiation of that one? We are going to get it as what? N x to the power of
x to the power of n minus 1.
Yeah, x to the power of n minus 1. That is what I am writing here. So therefore, this part, whichever we have in place of n, we have k minus r. K minus r as it is, we are writing. In
Hello, sir.
Sir, are you there?
I think net problem.
I think we lost him. I don't know.
Sir, we couldn't able to hear you.
I think net problem. From the place where sir is operating, there is no network.
I guess we lost him.
I think post.
So maybe the internet connection has been disconnected. So
Yes,
that is
sir. Yes, sir.
terminated. Once again, I'm connected.
Yes, sir.
So here in Ambedkar University, it is there is no signal here. I'm in university now. Right.
Yes, sir.
So now you're able to see this screen?
Yes, sir.
Yes, sir.
Yes, sir,
Yes.
we can.
Yes, sir.
So anyhow, we have got this d by dx, this one. Then after this by dx square, we are going to get once again by differentiating with respect to the x, the above equation. So therefore, this summation of r is equal to 0 to infinite as it is there, and this ar as it is we are writing here, okay. And to the power of so differentiation of x to the power k minus r minus 1. So we are writing it as a k minus 1 and x to the power of k minus r minus 2, because if you getting n minus 1, so it will be k minus r minus 2. So this is the second differentiation, that is d square y by dx square we have got. So this is the equation 3 which we have. Now we have the value of y, we have value of dy by dx, that is the first derivative, and the second derivative values we have. So these three values, y, dy by dx, d square y by dx square, all these
Sir, internet problem.
Internet problem. Hey, Soumya Ranjan bhai, apanko ye to ଟିକେ ଦିଅନ୍ତୁ phone number
here
ଟା.
we have
Okay.
we don't have any
Okay, okay.
don't have internet here. Even with my mobile I'm connected, so there is no signal proper here, right? So now you're able to see this.
Yes, sir.
Yes.
So this equation 4, whichever we have, like d square y by dx square, equation 3 is dy by dx, equation 2 is y. So all the values of y, dy by dx, d square y by dx square, all these three values we are going to be substitute in the equation 1. So this is the equation 1 which we have. We assume that Legendre's differential equation, that is a 1 minus x square d square y by dx square minus 2x dy by dx plus n into n plus 1 into y is equal to 0. In this equation, we have the values. So if you substitute here, The first one we have is 1 minus x square that we have written here. And the value of d square y by dx square here we have. That is the equation 4 here going to be substitute here. So if you substitute here, that is a summation of r is equal to 0 to infinite, ar into k minus r into k minus r minus 1 into x to the power of k minus r minus 2. So this is the value of d square y by dx square that we have substituted. Minus 2x into dy by dx minus 2x into dy by dx. So here in place of dy by dx, we are going to be substitute this equation 3 here. So if you substitute there, we are getting it as 2x into dy by dx value is summation of r is equal to 0 to infinite ar into x k minus r into x to the power of k minus r minus 1 we have. So then after, the third term whichever we have in this equation 1 is n into n plus 1 into y is equal to 0. So in that place, if you substitute here, plus n into n plus 1 here, the third term, into y value, we have assumed that y is equal to summation of r x to the power of k minus r. That here we have substituted. So this r value is equal to 0. Now from this equation, we can rearrange the terms. That means we will be writing in one order. So first we'll take in all these three terms. In the first term here, r is equal to 0 to infinite. The second term we have this one. In the third term also we have this one. So we have been taken out this one. Summation of r is equal to 0 to infinite. So this term here, this entire equation we can rearrange as k minus r into k minus r minus 1 x to the power of k minus r x to the power of k minus r minus 2 that we have written, minus, so this the last term and the second term whichever we have, that we can write it as in this form, that is k minus r into k minus r minus 1 plus 2 into k minus r minus n into n minus n plus 1. So this one we have. So we have taken minus actually outside. So the terms remain 2 into k minus r minus n into n plus 1. So x to the power of k minus r into ar is equal to 0 we are going to get here. Okay. Therefore, if these terms whichever we have here, so these terms again we are rearranging these all terms. So we are going to get this one, n into n plus 1 minus k minus r minus k minus r1. So here simply in place of minus we have written plus, and so that we, if you multiply, we are going to get this term, this entire term we are going to get into ar. Ar is for all this term from here to here, whatever we have for this one, 0 you are going to be get here. So now this equation 5 whichever we have got, so this we call it as a equation of identity we are going to be call. So what we are going to be call? We are going to be call it as an equation of an identity we are going to be call. So therefore, in this equation of identity, all the coefficients of powers of x, that means the power of k minus r minus 2, otherwise the coefficient of x to the power of k minus r. So what we have to do is we should be equate them to 0. What we have to do? We have to equate the coefficients of various powers of x to the power of k minus r minus 2 into and the x to the power of k minus r. We have to equate to 0. Why we have to equate to 0? Because this equation 5, whichever we have, this is the equation of identity. This is the equation and identity. So therefore, we have to equate to 0. So therefore, first we'll put the coefficients of x to the power of k to 0. Okay, x to the power of k to 0. So by substituting r is equal to 0. So what we are doing? We are substituting r is equal to 0, and we are making the power of k as 0. Substituting r equals 0 in this second term whichever we have. In the second term r we are making this part we are making to 0. So it will be x to the power of k. So the remaining what we have the coefficients is n into n plus 1 minus k minus r into k minus r plus 1. So that is what we minus a k, and in place of here k minus r plus 1, we are getting it as a k plus 1 into r value as we have taken to 0. The r value we have taken to 0, so we are going to get it as a0. We are going to be get. So final equation we are going to get it as n into n plus 1 minus k into k plus 1 0 we are going to get. So already we have told that when we have written this equation, that is a solution whichever we have assumed, we assume that a0 will not always equals to 0. A0 is not equals to 0. That is what we have assumed. So that by taking this a0 is not equals to 0, since a0 is not equals to 0, so this term always not equals to 0. So what we have remained, the term is n into n plus 1 minus k. So as it is a naught is not equal to 0, in this equation you see this, in this equation whichever we have got n into n plus 1 minus k into k plus 1 whole into a naught is equal to 0. So we get two either a naught is equal to 0 or n into n plus 1 minus k into k plus 1 is equal to 0. We can get two things, but we should not equate a naught is equal to 0, because already we know that a naught is not equal to 0. So therefore the remaining term we have is this one, n into n plus 1 minus k into k plus 1. So this should be equated to 0. So once if you equate this to 0, that is n into n plus 1 minus k into k plus 1 is equal to 0. So simply by multiplying here n into n, we are going to get it as n square, and here n into n plus n you are going to get, and in this equation we are going to get it as a minus k into k square, and here we are going to get it as a minus k is equal to 0. So that is what we have written this equation as n square minus n minus k square minus k is equal to 0. That is what we have written. So in this equation, I can write it as n square minus k square as one term and n minus k as one term we are going to write. So that should be equal to 0. Therefore, this n square minus k square is nothing but it is in the form of a square minus b square. So that is we can write a square minus b square as a plus b. We can write. So therefore, in place of n square minus k square, we have been written n minus k into n square minus k square. We have written n minus k into n plus k plus n minus k is equal to 0 we have. So therefore, from this equation, whichever we have written n minus k into n plus k plus n minus k. So here we'll be taking n minus k out. So here we are writing it as a n plus k plus 1. Okay, n plus k plus 1 we can write. So this, if you write, we can write it as this one, n minus k into n plus k plus 1 we can write. So in this equation which is equal to 0, either we can write n is equal to 0 one condition, n is equal to k one condition, or k is equal to minus n plus 1 we can write. So two things we are going to get from this equation, either n minus k is equal to 0 or n plus k plus 1 is equal to 0. N minus k is equal to 0, we can write it as a n is equal to k we can write. So from this equation, n plus k plus 1 whichever we have equals 0. So we can get it as a k is equal to minus n plus 1 we can get, because n if you go to the right side it becomes minus n. This plus 1 if it is going to right side it becomes minus n. So we have taken minus n outside. So we can write it as k is equal to minus n plus 1. So therefore we have got k is equal to n one condition we have got. Another condition what we have got, k is equal to minus of n plus 1 one condition we have got. So again here we will equating the coefficient. We have equated x to the power of k is equal to 0 we have been taken, and next what we are doing is here we are equating x to the power of k minus 1 is equal to 0 in this one. Okay, so now if you equate x to the power of minus k1 to 0, how it is going to be, we will be putting simply r is equals to 1. So if you put r is equals to 1 here, what happens in this equation? It becomes k minus 1 it is going to be get. Okay, k minus 1 here. R is equals to 1 if you put here in this equation. X to the power of k minus 1 it becomes. So therefore, if this equation 5 becomes as in this manner. So all only coefficients we are writing. Remember that only coefficients.
Hello.
0 by putting r is plus 1, that is what we have written, minus k into k minus k minus 1 into k. So because r value we have been taken as equals to 1, so r value we have been taken as equals to 1. So therefore it will be n into n plus 1 minus k minus of k minus 1 into k into a1 is equal to 0, because in place of r we have taken a1, r we have taken it as a 1, so it becomes a1. So therefore here this if you multiply and rearrange, we can get it as n into n square, we are going to get n into 1 n we are getting here, and here minus k square and plus k you are going to get into a1. So in this is the equation which we are going to get here. So in this again you see, if you rearrange the terms, the one terms we can write it as a n square minus k square, this one plus n plus k we can write into a1 is equal to 0. Again, you know that from a square minus b square formula, we can write it as a plus b into a minus b, that is n plus k into n minus k into n plus k into a1 is equal to 0. This is what. Again, in this one, if you see n plus k into n minus k plus 1 we are going to get. So here into a1 is equal to 0. So therefore here we know that this value n plus k into n minus k plus 1 is not equal to 0. This value is not equal to 0. So therefore the remaining term whichever we have is a1. A1 is equal to 0. So in the previous term, a0 is not equal to 0 here. If you see in this equation, here whichever we have when we have taken r is equal to 0, there a0 is not equal to 0. So here a1 value will be equal to 0, as this value is not equal to 0. We have to obtain the general relations of series. One more term is there, no, here the first term k in this equation 5, x to the power of k minus r minus 2. So for that also we have to equate to 0. So now we will be equating this coefficients of x to the power of k minus r minus 2 to 0. So if you equate to 0, the coefficients of this equation 5 whichever we have, k minus r into k minus r minus 1, all these. So there we are getting as equation as k minus r into k minus r minus 1 into ar. The second whichever we have, in that we are going to get it as n into n plus 1 minus k minus r minus 2, because k minus r we are equating the coefficient of x to the power of k minus r minus 2. So this we are going to get. So this entire equation we are going to be get here. So in this we have to find out the ar plus 2 value. So if you want to find out the ar plus 2, simply ar plus 2 will be as it is, which is equal to be taking into the right side. So it becomes minus of k minus r into k minus r minus 1, and this term will be going into the denominator, that is n into n plus 1 into n into n plus 1 minus k minus r minus 2 into k minus r minus 1, and this you have ar term. So this is the ar term which we are going to get here. So now this entire term, this one whichever we have, like k minus r minus 1, k minus r minus 2 minus n into n plus 1, this denominator term whichever we have, that we are writing. So this one n into n plus 1 minus k into k minus r minus 2 into k minus r minus 1. So that is the term whichever we have written here. Okay, just reverse we have written. So minus we have taken outside, so it will becomes plus. So we have written. So this term we can write it as in this manner: k minus r plus n minus 1, okay, into k minus r minus n plus 2. So if you want to know whether it is correct or not, just simply you add all these and multiply this. You are going to get this one. Okay, so therefore the denominator term we are getting it as this one, k minus r plus n minus 1 into k minus r n minus n plus 2. So that is what we have substituted here. So in the numerator we have line. So that is what as it is we have written here. Here as it is we have written here. Okay, and in the denominator term whichever we have, this one n into n plus 1, this one we have been written as k minus r into plus n minus 1 into k minus r minus n plus 2 we can write. So this is the equation 8 we have got. So now this equation 8 whichever we have got, in this equation. So by putting r is equals to 1, we are going to get a1. So that a1 is equals to 0. Therefore, this equation 8 is going to be get it as in this manner. Okay. So here we are going to get as a1 is equals to a3 is equals to a is equals to a7. All the odd multiples of a, like a1, a3, a5, a7. All these values are going to be get it equals to 0. A1, A3, A5, A7, A9, all these you are going to get. Only like the different values like A2, A4, A6, all you are going to get certain values. So now here, this equation whichever we have got, AR plus 2 here, okay, AR plus 2 whichever we have. So this we can get two conditions you are going to be get. Two conditions you are going to get here. Like in the case 1, we are going to get it as a in k is equals to n, we are going to get one value, and here we have similar is k is equals to minus n plus 1. Okay, so we are going to get two different values. So when we take k is equals to n here, okay, in this equation 8, k is equals to n, if you take, we can write it as ar plus 2. We can write it as ar plus 2. And here, in place of k, n, we are writing n minus r and n minus r. Is someone, do you have any doubt?
No, sir. No, sir.
Sir, proceed on.
Someone raised hand. That is the reason why I'm asking. Do you have any doubt, Soumya, Ranjan? Okay, if you don't have,
So
okay.
that raised
No,
hand
sir.
is from starting of this session. The sir has raised the hand from the starting of this Zoom class.
Okay, okay, no problem. Right. So here, this equation 8, we can write when we take n k is equals to n. You see k in place of k, we are substituting n. So it will be n minus r into n minus r minus 1. In the denominator, we are going to get it as in this manner, 2n minus r minus 1 into minus r minus 2, we are going to be get into ar as it is, this we are going to get here. Okay. So this also we can write in this manner, like a minus of n minus r into n minus r minus 1 divided by 2n minus r minus 1, r plus 2 we can write. Outside. So we are going to get this as r plus 2 in place of minus r minus 2. We are getting it as a r plus 2. We are going to get into ar. So now here the values of r we can substitute 0, 2, 4, and so on. Okay. So if you substitute 0 to only like even multiples 0, 2, 4, 6, 8, 10, if you substitute. So because if we substitute why we are substituting only 0, 2, 4 r, because all
Because they are not equal to 0.
Yeah, they are not equal to 0. Equals to 0. You see equation 9 here. A1 is 0. So that is the reason why we are not substituting those. So only we are taking 0, 2, 4, and so on we are taking. So if you want to get this A2, simply if you substitute r is equal to 0, we are getting A2. So A2 is nothing but r we are substituting as 0. So here we are getting it as n. Here we are getting it as n minus 1. See, we are getting it as a 2n minus 1 because this value becomes 0. 2n minus 1 we are going to get, and this one we are going to get it as a 2. This is what we have substituted, and AR whichever we have A0. So like this. Get. So if you want to get A4 value, what we have to substitute? We have to substitute R is equal to 2. So therefore we have as a 8, right? Similarly, this we have got already. We know the A2 value. So A2 value what we have into 2n minus 1 in the denominator.
By
2n
minus 1 into 2.
So after substitution, we are getting it as A4. So A4 value we are getting it as a n into n minus 1 into n minus 2 into we are getting it as a 2n minus 1 here, 2n minus 3 here. It is there 2n minus 1 into 2n minus 3. Here we have 2, here we have 4. So therefore it will be 2 into 4 into A0. This is what we are getting it as a A4. And similarly, we can get A6 value as this one. Okay, this entire equation we are getting it as A6. So similarly, you can get the value of A8. Okay, A8 you are going to get A10. So by substituting different values of R, we will get A2, A4, A6, and so on. We are going to get here. So this is what we have. So therefore, as we know that A1, A3, A5 are all zeros, so we won't get those values, right? So substituting the various values of A, we have assumed as a solution here in the starting. This is a solution whichever we have been assumed. So by substituting all the values of A's whichever we have, like A2, A4, A6, and so on, by substituting all the values of A in the equation 2, so we get the solution for K is equals to N. We get the solution for K is equals to N as in this form we are going to get. That is Y is equals to A0. Okay, A0 into x to the power of n minus n into n minus 1 divided by 2 into 2n minus 1 x to the power of n minus 2. Someone unmute yourself. You're getting so many sounds. Right. So and so on, x to the power of n minus 4, and next you are going to get another term which is x to the power of n minus 6, and so on you are going to get. Okay, so this equation actually the solution for Legendre equation when we consider that the condition K is equals to n. So now you understand why we have written K there. K is nothing but n. So n values will be taken from 0, 1, 2, 3, 4, and so on. So the solution. So now here A0 whichever we have been taken is an arbitrary constant. Okay, here, and the n value whichever we have is a positive integer like 0, 1, 2, 3, 4, and so on. Positive integer we are going to get. So if A0 value is this one whichever we have taken 1, 3, 5, and so on up to 2n minus 1 by n factorial. So therefore if you substitute A0 value in this one, we are getting it as this equation, that is Pn of x, okay, is equals to, in place of A0, 1 into 3 into 5 into 2n minus 1 divided by n factorial. And already we have this entire term, the equation 10, which we have is x to the power of n minus a. So this is the whichever we have K is equals to n. We have another condition also, K is equals to n minus of n plus 1. Here we have seen, no, in this one we get two conditions, K values. Okay, so K values we are going to get K is equals to n1 condition, another one is K is equals to minus of n plus 1. Another condition here, you see equation 6 whichever we have. From this equation 6 we can get K is equals to n1 condition we are going to get. Another condition is minus of n plus 1. So now second condition we are going to take, that is K is equals to minus of n plus 1 we are going to be take. So that is what we call it as a case 2. Okay, so by taking this condition K is equals to minus of n plus 1, we have equation 8 where AR plus 2 value we can write it as in this manner. So I'll give the notes, you go through this one. So equation 8 whichever we have, see here, this one AR plus 2 value. Okay, So there are k value, we are going to substitute n minus n plus 1. So therefore, we are going to get this equation k plus 2 value we are going to get in this manner. N plus r plus 1 into n plus r plus 2 divided by denominator r plus 2 into 2n plus r plus 3 into ar. So this is the equation 8, whichever we are going to get. So this is the condition arised by taking k is equals to minus of n plus 1. Okay. So this condition, in this condition, we'll substitute the values of r 0, 2, 4, 6, and so on. We are going to substitute. So therefore, we are going to get a2, a4, a6, all these values we are going to get. So a2 value we are getting in this manner. That is when we substituted r is equals to 0 here. So what it remains? N plus 1. So that is what we have got, n plus 1. So here r is equals to 0, n plus 2. N plus 2 we have got. The denominator r plus 2. So it will be 2. So here r is equal to 0, therefore it will be 2n plus 3 into ar means a0. This is the a2 condition is a is equals to minus of n plus 1. Similarly, we can get the a4 value as this into a2. So a2 value already know this is the value which we have got. So by substituting a2 value this, we are going to get this a4 value as in this manner we are going to get. That is n plus 1 into n plus 2, n plus 3 and into n plus 4.
Hello?
Into this value is a0. This is a0 we have. Right. A0 we have. So now we know that a1 odd multiples are equals to 0. That is a1, a3, a5, all these values are 0. So therefore, we won't take those values. So by taking these a2, a4, a6 values, the solution, whichever we have written y value for k is equals to minus of n plus 1, we are going to get in this manner. This is the equation which we are going to solve. Okay. So this condition, whichever we have got, y is equals to this value by substituting a naught is equals to n. This one, the solution, whichever we are will be calling it as a Legendre's function of second kind. Okay, so which we can denote y is equals to qn of x. So you have to assume, you have to remember that if they are asking the Legendre's function of first kind, you have to assume that the condition is k is equals to n. That equation you have to write. If they are asking the Legendre's polynomial of second kind, you have to take the condition k is equals to minus of n plus 1 and you have to substitute, you have to get. So case 2, whichever we have got, we will be calling it as a Legendre's function of second kind and it is denoted by qn of x. So this is what we have, equation 13, whichever we have. So therefore, if you want the entire, so someone raised again, Rajnikant.
Sir.
Yes,
sir. Can you hear me, sir?
Yeah.
There is an error in this case 2, sir. 2n minus 3, it should be 2n plus 3.
Which one in the equation?
Here, in the equation, in the y equal to a0, in this equation, this must be 2n plus 3.
2n plus 3 here.
Yes, sir.
Yes. It is 2n plus 3. Yeah, I have written minus. Okay, you can correct it. It is 2n plus 3 actually. So I have written. So here it is corrected. In the equation 13, you see.
Correct.
Yes, sir.
Here it is correct.
It is corrected. There.
Okay.
Minus 3. So this we call it as a Legendre's function of second kind. We are going to be called qn of x. So therefore, we have got two conditions we have got, like a solution of Legendre's equation we have been taken. One is Pn of x we have got, another one is Qn of x we have got. So therefore, the general solution of this Legendre equation can be expressed in this form. How we can express? Y is equals to a into Pn of x plus b into Qn of x. So Pn of x is when the condition k is equals to n. Qn of x is the condition when we have taken k is equals to minus n plus 1. So the combination of first kind and second kind will give the general solution for the Legendre's equation. So therefore, we can write y is equals to capital A into Pn of x plus B capital B into Qn of x. So here AB, whichever we have here. So this AB, we are going to be call it as an arbitrary constants. What is that? We are going to be call it as what? Arbitrary constants we are going to be called here. So this is about the Legendre's differential equation and the solution of this Legendre's polynomial. Okay, Legendre's polynomial solution we have. Right. So then after we'll move to next topic, which we call it as a generating function of Legendre's polynomial. Okay. So generating function of Legendre's polynomial. Just 1 minute. Right. So this Legendre's function. So Pn of x we have to take 1 minute. Up to this class up to 230. Up to 12. Okay. So we'll finish this what we call Legendre's function of Legendre generate. Take this Pn of x. Okay. So what we have to show here it is, we have to show that Pn of x is the coefficient of z power n in this expansion. That is 1 minus 2xz plus z 2xz plus z square whole to the power of minus half in ascending powers of z, that we have to show. Okay. So therefore, this is what we call it as a generating function of Legendre polynomial. So we can write this 1 minus 2xz plus z square minus half as 1 minus z we have taken outside from these two terms. Okay. So it will be 2x minus z whole to the power of minus half we have. So now this is in the form of binomial expansion. Means otherwise we can say that in the form of binomial theorem 1 minus x whole to the power of minus half. So that we can write in this binomial theorem as 1 plus x of n. So we can write it as a 1 plus nx plus n into n minus 1 by 2 factorial x square plus n into n minus 1 into n minus 2 by 3 factorial x cube and so on we can write. So therefore, the term whichever we have taken 1 minus z into 2x minus z whole to the power of minus half. Here we are writing as this one 1 plus, because it is minus here it is there. So here in this term we have plus. So plus this term n is nothing but minus half. So we are writing it as a minus half here. It becomes plus half into, in place of x we have this one z into 2x minus z we have. Okay, that is what we have written. And next term is this one n into n minus 1. So n value is 1 by 2. N minus 1 it becomes 3 by 4. So this term also becomes plus into what we have x square. Okay, x square is nothing but z square into 2x minus z whole square by 2 factorial. So 2 factorial is nothing but we have written as a 2. This one we are going to get, and so on. We'll get as 1 into this. If you expand continuously, we are going to get it as a 135 into 2n minus 3 divided by 246 into 2n minus 2 and z to the power of n minus 1 we are going to get here. Okay. So therefore, the final term is this one 2x minus z whole to the power of n minus 1 and 135 and so on up to 2n minus 1 divided by 246 into 2n. This z to the power of n into 2x minus z whole to the power of n. This we are going to get here. So simply this equation, whichever we have, this we have been expanded in the form of a binomial theorem. By taking this binomial theorem, we have been expanded and we have got this equation 1. So this is the expansion in the form of a binomial theorem. So this is the equation we have got. Now what we have to do, we will take the coefficients of z power n. So that is coefficients of z power n is nothing but this one 1 into 3 into 5 into 2n minus 1 by 2 4 6 into 2n z to the power of n into 2x minus z to the power of n. So the coefficients of this we have to take. So if you take this, that is what we are going to get 1 into 3 into 5 into 2n minus 1 divided by 246 into 2n. And here, in place of this, we are going to get the 2x to the power of n, we are going to get. Okay. So this value, we can write it as this one. We have expanded 2x whole to the power of n as 2 power n, x power n we have been expanded. Now here 1 into 3 into 5 and so on 2n minus 1 into x power n you are going to remain, because this 2 power n and this 2 power n both it is going to be get cancels. So it will be 1 into 2 into 3 up to n means we can write it as n factorial. So we have taken it as equation A. Now similarly the coefficients of z power n, okay, in this equation, that means here we have so here this one, okay, see this one 1 into 3 coefficients of z power n if you want, okay, coefficients of z power n if you want. So simply we'll write that coefficients of z power n as this one we can get, because if we want to get the coefficient of z power n, so we can write it as this equation 1 into 3 into 5 and so on, this entire thing. So we can write this as in this form we can write, okay, 1 into 3 into 2n minus 1 2n minus 3 into 2x minus z whole to the power of n minus 1. This week if you expand we are going to get in this form, e form, this form we are going to be getting here. Okay. So after getting this one, so what we are doing is simply we are multiplying and dividing this equation with 2n minus 1, okay, by n. So we are multiplied and divided by with this one 2n minus 1 by n. Okay. So here you see, if you multiply and divide, we are going to get this as n into 2n minus 1. So therefore, this equation, whichever we have, so 1 into 3 into 5 and 2n minus 3 into 2n minus 1 up to here we have written, and this is nothing but we have been divided with this 2n minus 1 by n. So we can write this as n factorial, we can write. The term here, whichever we have, we are writing is same. It is n into n minus 1 by 2 into 2n minus 1 x to the power of n minus 2. So this equation we have taken as a P. So similarly, we want to get the coefficients of z power n of n minus 2. Okay. N minus first one we have taken the coefficients of z power n we have taken, and next one we have taken the z power 2x minus z whole to the power of n minus 2 we have been taken, and similarly we are getting the coefficients of z power n in this term. So ikkada vastundi. So that is the final equation which we are going to get, the three terms whichever we have. So the coefficients we are going to get this one. So therefore, if you proceed further continuously, if you proceed, we can get like the coefficients of z power n as in this manner. So in the outside, whichever we have, we are going to get in this manner 1 by n factorial. The terms powers whichever we have. So in the equation A is this one, equation B is this, equation C is this one. See equation C, what we have, this entire term n into n minus 1 into this one. So that is what we have written inside. This entire term we have written outside. So for equation A, B, C, similarly. So this we are going to be call it as, which is equal to Pn of x. Okay. So thus we can say that the expansion, what is the expansion we have taken? 1 minus 2xz plus z square whole to the power of minus half. Okay. All the coefficients of z square, z square, z cube and so on will be like P1 of x, P2 of x, P3 of x. Okay. First coefficient z then P1 of x. So P1 of x is nothing but in place of n, we have to substitute 1 in the equation load. If you want P2 of x, in place of n, we have to substitute 2. We get the equation of P2 of x. So we'll get this P1 of x, P2 of x, and so on we can get. So avanni raaste em ostundante manaki equation this value 1 minus 2xz plus z square whole to the power of minus half as 1 plus z P1 of x, z square P2 of x, z cube P3 of x, and so on, z power n of Pn of x we are going to get. So we can write as a summation of n value will be starting from 0 to infinite. Okay, it's positive integers we have. So n is equal to 0 to infinite. So So this is z power n Pn of x. So z power n Pn of x we have been written. So now this is the what we call whichever we have seen is a generating function of Legendre's polynomial. So what is the generating function of Legendre polynomial is we have to show that Pn of x is the coefficient of z power n in this expression, otherwise in this expansion. So that is what we have seen here. Okay. So do you have any doubt, any one of you?
Yes, sir. Yes, sir.
Hello.
Sir. Sir, can you hear me?
Yes.
Sir, can we write the solution of Legendre polynomial in both ascending and descending power of x?
Which one?
The solution of Legendre polynomial, can we write in both ascending power of x and descending power of x?
Yeah, we are writing only this one, no, ascending power.
Sir, is the descending power have more physical significance? I have read it somewhere that descending power of x have more physical significance than ascending power of x.
Yeah, but here we are wrong. Can you?
Your voice is not coming, sir. Your voice is breaking.
Yeah, tell me.
Sir, I have read somewhere that the descending power has more physical significance. I am not. I cannot get the sentence. It is properly written in the book that the descending power of x has more physical importance than ascending power.
We have only this, no? Ascending power we have. Descending power we don't have now. So
okay.
If we have, we will see later. Okay. Okay.
Okay, sir.
Right. So this is the what we call for Legendre's differential equation.
Generating functions of Legendre equation.
Okay. So basing upon unable to listen your voice. Right. So basing upon this, whatever simply we will substitute x is equals to 1. What actually we have equation is this equation, no? 1 minus 2xz plus z square whole to the power of minus half. We have got it as a summation of n is equal to 0 to infinite z to the power of n Pn of x. So we have to show that Pn of 1 is, yes? This is the problem which we have. So simply if you substitute x is equals to 1 here in this equation, right? So if you substitute x is equals to 1, it will becomes 1 minus 2z plus z square whole to the power of minus half. So in the RHS, n is equals to 0 to infinite, z to the power of n, Pn of 1 we have. So therefore, it becomes what? It is in the form of a minus b whole square, 1 minus 2z plus z square. So we have written 1 minus z whole square whole to the power of minus half. And in the RHS, we have been expanded this one so that we have got 1 plus z P1 of 1, z square P2 of 1, z cube P3 of 1, and so on we are going to get. So in the LHS, if you see this 2 into minus half, so it becomes 1 minus z whole to the power of minus 1. So in the RHS, we have written the same thing, we have been written. So now we'll expand this by using the binomials theorem. So we expand this using the binomials theorem. So we'll get these terms. That is 1 in plus minus 1 of into minus z. The next term we are going to get minus 1 by 2 factorial and so on we are going to get. So this on the RHS we are writing it as a summation of n is equal to 0 to infinite Pn of 1 into z power n we are going to write. So in the LHS the first term is 1, the second term we minus into minus plus z we are going to get. Here it will be minus 1 minus 2 into minus 1 it becomes plus 2 divided by 2 factorial. This entire term whichever we have, this we are going to get as a, this is 1, this is minus 2, this is minus 3 you are going to get. So minus into minus plus, plus into minus. So only this plus you are going to get 1 into 2 into 3. Because here we have odd multiples, so it is minus term becomes plus. So it is plus 1, 2, 3 z cube by 3 factorial. And the RHS same we are writing. So therefore, If you see 2 by 2 factorial is 2, this is 3 by 3 factorial, 1 into 2 into 3 by 3 factorial is 1. So the LHS term we are going to get it as a 1 plus z square and so on up to z power n you are going to get, and the RHS we have this one. So therefore, if we equate the coefficients of z power n in the both sides, see here, this is the z if you have, okay. So here P1 of 1. So what is P1 of 1? We have 1. This is the coefficient of z is 1. Here the coefficient of z is P1 of 1. So that is Pn of 1. We can P1 of 1 we can say that 1. So here P2 of 1 is the coefficient of z square. So what is the coefficient of z square here? 1. So therefore P2 of 1 is 1. Similarly, Pn of 1 if you take, we are going to get it as a 1. So this is a small problem. They may ask in the short answers. Okay. So basing upon this, we have so many problems. So just I have solved some problems. So later on, I'll share these notes. You go through this one. So as for today, so just we have seen this. What is the generating function of Legendre's equation we have seen, and as well as this generating Legendre's differential equation solution also we have seen. So we have got two conditions, like k is equals to n, one condition we have got. Another one we have got it as a k is equals to minus of n plus 1 we have got condition. So for k, yes. Okay. So for k is equals to n, we will be calling it as a Legendre's differential equation of first kind. For the condition k is equals to minus of n plus 1, we will be calling it as a Legendre's differential equation of second kind. We are going to be called the overall solution of this Legendre's differential equation, that is the general solution. We will be calling it as y is equals to a of Pn of x plus b of Qn of x. We are going to be called, that is a general solution we have. Next, we have seen this generating function also. Seen for the generating function, we have solved, and we have got the generating function as a Pn of x we have been got. So basing upon that one, we have seen one problem also, that is Pn of 1 equals to 1 we have got. So as for today, we will stop here. Then in the next class, we'll see some more topics. Okay.
Okay, sir.
Okay, sir.
Okay, sir.
Thank you very much.
Thank you, sir.
Class.
Thank you, sir.
అవన్నీ నువ్వు అవన్న బుక్ లో టెక్స్ట్ బుక్ అంటే అవన్నీ నేను రాసిన ఆల్రెడీ, రాసిన నోట్స్ రాసి అవన్నీ స్కాన్ చేసి